welcome back to Journal Club. My name is James, and for this month's episode, we're going to step away from the AI research that we've been normally covering, and instead, we're going to engage in a bit of tasteful nepotism. Earlier this month, I went to Montreal to present one of my own publications, which was called A Modularized Framework for Symbolic Execution and Applications for Usable Tool Design. This paper is a systemization of knowledge that focuses on a powerful static analysis technique used in reverse engineering and vulnerability discovery called symbolic execution. This work won a Distinguished Paper Award at the conference me and my co-author submitted to, so it felt appropriate to showcase it on this platform too. To start, let's talk about what symbolic execution even is with a brief example, just to make sure that we're all on the same page. Symbolic execution is a static analysis technique that can operate on source code, binary files, or intermediate representation bytecode of the program. The power of the technique lies in its ability to reason about ranges of potential values for the inputs of a program. So, for example, let's take this program foobar here. It's a relatively simple function that takes two integers as input, and depending on their values, makes some changes to locally declared variables x and y, before finally checking that x minus y does not equal 0 on line 8. So while this program may seem pretty simple, it's still annoyingly difficult to properly test. So let's say we want to ensure that no input values that this program ever gets passed will cause this assert statement to fail. One approach could be that we would write test cases or run the program repeatedly with specific input values for A and B and observe how it affects the values of x and y. While this does technically work, this approach is obviously quite tedious and manual. Additionally, it's really hard to prove that you've exhaustively checked all possible values for A and B and ensure that you're not missing something that will cause it to fail. Instead of manually testing, another option would be to use another static analysis technique called fuzzing, where you automatically generate random inputs and run the program with random values for A and B. While this is somewhat better in terms of coverage and it's less manual, it has the same problem of not knowing when you're really done, as does manual testing. Additionally, randomly selected values for B are going to be extremely unlikely to get past this guard statement on line 5. So it's extremely unlikely that the code later on 6, is ever properly tested. If we instead used symbolic execution, the inputs A and B would be represented as symbols, so sigma A and sigma B. Initially, these symbols would have no restrictions as we're at the start of the program. But as a symbolic execution engine walks through the code, it will track any instructions that impose restrictions on these symbolic variables. So in this case, you can see that on line 3, we had a branching condition on whether or not A is equal to 0. At this point, the symbolic execution engine could fork into two different states. One where A is not 0, and execution continues to line 4, and one where A is 0, and execution instead jumps to line 8. Each resulting state would have different saved symbolic constraints tied to the value of A, and a different set of path constraints depending on which route we actually went. This is the same process that would happen again on line 5, this time splitting into two more paths based on the value of B. These constraints would be saved in addition to the prior ones saved on A. So as you can imagine, the complexity can get out of hand very quickly. Unfortunately, symbolic execution suffers the same several limitations that have prevented its widespread adoption for its nearly 50-year lifespan. First up, the amount of memory needed to store all the different symbolic constraints and the amount of compute time it would take to systematically explore every portion of the code for complex programs is far too high. This is a commonly known limitation of symbolic execution known as path explosion. To illustrate it, if we look at our code example, this simple program will produce a surprising amount of symbolic state information. Just these 9 lines add this much complexity that needs to be stored by a symbolic execution tool in order to function properly. I know this is quite a bit to take in all at once, but this essentially comprises an execution tree of all the valid states for our program at every line with all the symbolic variables and their path constraints given which prior path conditions and route you traverse the code. If you use symbolic execution on larger code bases, the amount of symbolic state information or SSI, that you can see scales exponentially. Additionally, symbolic execution is not the most user-friendly technique. The majority of symbolic execution UIs, if they exist at all, are, in my opinion, a bit antiquated and unintuitive to set up and actually use. Additionally, due to the computational limitations for symbolic execution, it's not clear when it's done on larger code bases, as the tool can continuously be computing new test cases and inputs without a clear indication of how much progress has been made or how close we are to having finished scanning the code base. Lastly, due to the complexity of the analysis, symbolic execution cannot be easily applied to any language or framework. The majority of available tools that are immediately ready for use operate on C, C++, or Java, and while there is some effort to expand the technique to other languages like Rust, adoption on the whole is still quite low. Therefore, it's important to identify which new domains are actually worth the additional effort to bring symbolic execution to. So these limitations to symbolic execution have persisted for the many years that it's existed. So we wanted to take a step back and survey what the state of the literature is to get a sense of where we are, what has been tried, and where we should focus our efforts next. And to that end, we sought to answer the following research goals. So how can we enable the continued advancement for symbolic execution for itself within its existing applications? And how can we facilitate it to expand to new domains and maybe incorporate new analysis techniques as well to overcome its limitations? So to answer these goals, we conducted a broad literature review of nearly 300 papers from two different sectors: symbolic execution papers and developer and security professional user studies, which I'll refer to as DSP papers. For the SE papers, we wanted to capture the main technical contributions towards symbolic execution for each publication, along with how the technique was used, what information it relied on, and any additional techniques that were used in conjunction with symbolic execution. For our DSP papers, we looked for specific subtasks of debugging, code optimization, code comprehension, and vulnerability discovery. We also identified what information needs any of the participants in these studies expressed, along with their preferences for usability or functionality of security tools. To actually accomplish this, we qualitatively coded both bodies of literature with their own unique codebooks, and then found relationships between our codebooks based on overlapping information needs or use cases. Our SOK proposes a new framework to describe symbolic execution, define its functionality, and quantify the various improvements that the academic community has created over the past several decades. These different modules, as I'll refer to them, paint the full picture of how symbolic execution operates and can quantify the myriad of improvements we've witnessed. So, to go through them, first up, let's talk about the execution driver. This is the module that walks through the program line by line and checks for new symbolic constraints. In our foobar program, the execution driver is what actually moves us from line 2 to line 3, and then is responsible for orchestrating with the other modules to update any symbolic constraints, or maybe try and check to see if we need to solve any of them. The majority of the improvements to this module involved more intelligently choosing when to invoke symbolic execution in the first place to minimize incurred costs. The most technically advanced improvements we saw in this module involved instrumenting the program in question to reduce the number of symbolic variables and therefore reduce the computational complexity incurred when actually running the program. Next up is a search heuristic. This is concerned with managing the selection of different execution paths to investigate. Essentially, once we hit a branch condition, which way do we prioritize and go next? This could be something as naive, like depth first search, causing us to always go and follow the true case at each statement. The vast majority of the improvements made to the search heuristic try to tackle the path explosion problem by prioritizing different execution paths for testing. The idea being a different search heuristic will result in different parts of the code getting tested before we hit any resource constraints. There are a variety of creative approaches, including setting up machine learning models to predict the expected cost of exploring one path over another, and choosing the path with the lowest expected cost to get the most coverage as fast as possible. Next up is the symbolic state management module, which is responsible for allocating memory to store all the different symbolic path constraints or symbolic variables for the program. Essentially, this module is creating and managing our symbolic execution tree from earlier. We saw limited types of improvements in this module, but they typically were the most creative, such as defining new types of trees or data structures to efficiently store the symbolic constraints, or by intelligently sharing already allocated constraints across multiple execution paths that share or need the same information, therefore reducing the memory footprint. Next up is the environment and memory model, which sets policies for how the symbolic execution engine should manage any external environment calls like API calls or receive network data or memory reads from a file. These cases are tricky for symbolic execution typically because the range of values from these sources cannot easily be inferred or trimmed down by the code. And it incurs a high computational cost when generating test cases on values that can essentially have any value stored in them. Most of the improvements to this module are handcrafted and case specific to the program in question. However, they broadly fell into two categories: improvements to modeling external values and function stubs. Function stubs were the simplest improvement, where users can identify a system or function call in the program that produces repeatable results, say like a hashing function. And instead of having the symbolic execution engine execute over the entire complex hash function, you can simply create a stub that returns a random value, thus saving you a lot of time and energy. Lastly, there's a constraint solver, which is responsible for calculating specific values from our saved symbolic constraints. So in our example, this would happen every time we encountered the assert statement and need to verify that the symbolic constraints that we've collected along the way to this point do not allow for values that would result in a crash. From the constraint solver, you would get the typical output of test cases or concrete values that result in a crash that the constraint solver found. We saw a lot of research on simplifying constraints by pruning redundant components or pruning constraints that canceled each other out, or alternatively, change the representation of the constraints under the hood so that the solver can more efficiently calculate concrete values. We wanted to make symbolic execution more usable, but there wasn't a clear set of usability guidelines for security program analysis. Thus, we distilled the usability insights that appeared repeatedly across our DSP corpus into the 6 guidelines that you see here. I encourage everyone to check out our paper for more specifics about these guidelines, as many can apply to your own projects as well. But for brevity, I'll highlight 2 key findings. A common theme across the DSP corpus was the importance of configurable tooling to support users' workflows. Although symbolic execution is powerful, it's also incredibly complex. Most of the SE tools that you can download are like this highly complex tuned engine. Despite its power, it's difficult to set up and requires an expert to make any tweaks to how it functions. So future research in symbolic execution should focus on supporting configuration options for users, as well as providing reasonable defaults to lower the initial barrier to entry for actually setting up and running symbolic execution on your own codebase. Lastly, collaboration is a core part of the software development lifecycle. Careful attention needs to be paid to areas where creative tool design can reduce friction surrounding collaboration. This includes shareable configuration files or shareable intermediate results so that team members can reach a shared understanding of the symbolic execution output faster. Similarly, I believe there's a lot of really promising opportunity for integrating symbolic execution into the LLM software development lifecycle. This could be in the form of validating LLM-produced code, or by giving more concrete symbolic specs to the LLM that they must adhere to when producing new code. However, there's been little to no published research investigating the intersection between LLM-assisted coding and tooling and symbolic execution. Despite the various technical improvements to SE across all the modules, determining which improvement or configuration option to use for any given case is still a challenge. And this framework presents a unified vocabulary around symbolic execution and is the first step in lowering that barrier to entry for any future symbolic execution operators. Thanks for listening, and please contact me with any questions, and I'll see you all next time.